Oh, that's he's not coming here today.
I don't know.
My voice from here wrong. I would think Auburn. Yeah, I know we're done. Yeah, that's not. That he's not going to today. I'll try it on your own. Yeah. If you want to kind of understand. Right, that's very I can work there. Oh.
Okay, we're gonna get started for today. Hi, I'm Tyler. I'm a postdoc who works with Abhishek. I graduated from Berkeley recently, doing a PhD on control theory, which is what we're gonna mostly be talking about today. And just as a request, I'll try to keep track of time, but I sometimes forget to look at my phone. So if like 5 minutes beforehand, if someone could just like wave at me, that would probably be very helpful. So thank you. Okay. Okay, so just to sort of recap where we are in the class. So you've learned a lot about state estimation. And at the end of last class, you started getting your toes wet a little bit in control, and we're going to really sort of try to solidly make our first foray into really understanding what control is and trying to understand a few examples of like what is control, how do you use it, and how do you build a controller. Okay, so we're going to start off by just sort of recapping some of the things that were talked about at the end of last class. So let's just start off with the question that you were asked last time, which is what is control? Does anyone have any thoughts on just like what is control? What is a controller? Yes.
You have like a thing that you want your robot to follow. Um, Control is the way you make sure that it stays on that thing and making adjustments for hardware problems, for instance, and like the robot.
Yeah, exactly. That is exactly the answer you want to have. Right. So just to repeat that, right, it's we can sort of break down getting a robotic system to do the things that we want into, well, first perceiving where the robot is in the world, which is what you spent a lot of time learning about so far, then generating some sort of plan of what we want to do in the future, generating a controller, which then decides what commands we're going to put into our robot to get the system to do the things that we want. So just to sort of make this a little bit more concrete again. So again, a plan is something we want our robot to do in the future. So this would be, I want my car to be at certain points in time in the future. And then what a plan really is some representation of that thing that I want to do in the future. Okay, so there's many different representations you can use for plans. So you can sort of define this plan using a spline, but just keep in mind there's many different ways you can sort of represent the future and what you want your system to be doing in the future. And in particular, sort of the keywords we're going to be using today is we're going to be tracking some reference trajectory, which is just sort of some curve or some spline defining what we want our system to be doing in the future. Okay, and then this question you sort of talked about yesterday, which we're really going to try to hammer home today, is what is feedback control and why do you care about it? And so exactly as was just said here, the reason we want to do feedback control is because we're going to make mistakes when we're trying to get the system to do what we want in the real world. And to just sort of drive this home, let's say that I wanted to get this car to follow this path that I planned. And I have some simplified model, perhaps like a very simple kinematic car model, which is inevitably going to be wrong. So if I try to decide what these controls are, so these are the sort of motor commands I'm going to put into the system to sort of follow this path. If I try to decide that just at time 0 when my car is here, and I just sort of follow that sequence of plans blindly, what's inevitably going to happen is I'm going to make mistakes. I'm going to drift away from the plan that I generated. And so what we want to do is sort of correct for this. And sort of the keyword you want to take away from this is what's known as open loop planning, where you sort of just make a plan, you close your eyes, and then you never sort of pay attention to what's actually happening to your system. Okay, so now what feedback control is really trying to sort of be reactive and sort of make improvements to how you're controlling your system as you see how it's evolving through time out in the environment that you're actually encountering. So what this looks like is instead of just sort of blindly deciding what to do with my system, what I'll do is at every point in time, I will sort of look at where my system actually is in the world. I'll come up with some notion of the sort of error or the distance between where I am right now and where I actually want to be. And then what feedback control does is sort of incrementally at every instance of time, try to push my system back to where I want it to go. Okay. So again, we really want to be thinking about this as where do I want to go? How far away and what direction do I need to go to get there? And how do I push my system there? Okay, so again, just to sort of put these steps up on the screen, we're going to sort of walk through these steps for the car example for a lot of the lecture today. So step 1, we're kind of going to assume is given to us, and is something you'll spend a lot of time on later in the class, which is how do you generate this sort of reference or plan that you want to try to track? The next thing we're going to kind of assume is done, which you talked about a little bit at the end of last class, is coming up with a way of picking the point on the reference that you want to try to go to at any given instance of time. So you talked about 2 possibilities for this at the end of last class. Does anyone remember what 2 of those possible ways of picking a point on the reference were? So I'll give you maybe the easy one, which is just the nearest point on the reference. So just take sort of like the distance, which is the point on the reference, which is the shortest distance from where I am. Do you remember another one, maybe? Yeah. Yeah, exactly. Right. So the next one we did is we sort of instead of just going to the nearest point, we go to a point which is a little bit ahead of where I am, so that I sort of make progress along the track while I'm trying to get there. And what I'll mention is we're going to sort of abstract that out for the purposes of this lecture, but there's many, many different ways you can do that. So where we're going to spend sort of the meat of the lecture today is going through an example of how we actually go through computing this error to measure the distance from where I am to where I want to be and then actually computing a controller, which gets you there. So one thing I'll mention is like they're sort of written down as like 1, 2, 3, 4, by hand, do these things. And I think one thing that's really confusing when you first learn control is that like uh, I'm just going to come up with some like tracking errors, and you're going to be like, where did you come up with that? How did you get that? And then I'm going to propose a controller, and you're going to be like, well, where did you come up with that? And I think just one thing to understand is that in the real world, you spend a lot of time trying out different ideas for each of these 4 steps. And oftentimes it's not necessarily 1, 2, 3, 4, because these are sort of very interwoven decisions. And people spend a lot of time thinking about how to do these in smart ways. And so if it seems like a little bit of black magic, I think just trust that like as you sort of play around with these things and get more experience with them, it'll sort of be more intuitive how to do all these steps together. Okay, so we're going to talk about what is, I think, a sort of like relatively simple example of like, right, how do I get a car to follow a path? But I think just to give you some idea of what you can do with these tools that we're going to build up today, I'm going to play a video from some of my collaborators at Berkeley, where they took quite literally the tools you're going to learn today. And what they did is they got this bipedal robot. So this is a robot with 2 legs to ride these little hoverboards. So if you've never seen these things before, basically they're like these 2 platforms with a motor and a wheel under them. And you try to balance on it, and basically you lean forward a little bit, and that sort of kicks the motor into gear and drives you forward. Like really stupidly hard to actually control and actually stay on. So I didn't make it onto the video, but it's actually really hard to get a robot to do these things. And so yeah, what they did is it's very complicated. This is a very high dimensional system. There's a lot of things going on with it. But really what they did is they broke down the system in the way we're going to today, where you sort of generate a plan for what you want to do. In this case, is keep my robot upright and move forward at some desired velocity. You generate a reference, and then you design a feedback controller, which tries to keep you on that reference. So I actually just really quickly, want to replay that last little bit right there, because I think it gives you sort of a very good visceral understanding of what feedback control is. Okay, so up until this point where we have this disturbance, everything is going to plan, right? So our controller is doing great. And then this thing which I didn't plan for, my model comes in, i.e. this foot came and sort of kicks my robot off of its reference trajectory. And then what you're going to see is the feedback controller kick in and do its job. Okay, so that's sort of very the sort of recovery behavior where what the controller is doing is sort of jostling and dealing with the physics of the system and sort of reacting to these disturbances to get the system back to the point where we want is what we're really going to try to understand today, how we can build up controllers which do that. Okay. Okay, so next what we're going to do is for our car example, we are going to go through trying to understand, given a reference point, which we're going to know with the subscript ref on our reference trajectory, and given the point in the world where my car actually is, which we're going to be denoting with some coordinates x, y, and some heading theta, how can I go about actually computing some sort of reasonable error between where my system is and where I want it to be. And so I guess real quickly, does anyone have any like thoughts or any proposals for just like a natural way of defining what this error could be? Yeah.
Each plate. X reference from X and then square it?
Yeah, no, that's a great idea. So we're going to propose something which is a little bit fancier for the system, but exactly what you described is actually sort of the most natural way, and actually we use that for a lot of systems. So maybe now I'll propose one which is a little bit more involved, where what I'm going to do is instead of just sort of adding and subtracting the Euclidean distance between the X and Y coordinates, what I'm going to do is I'm going to sort of represent this error in a way that makes sense for my reference, i.e. in a way that makes sense sort of with respect to the motions that I want to be generating. So what we're going to do here is we're going to sort of define a coordinate frame around our reference trajectory, and in particular, the point on the reference trajectory where we're going to try to go. So what I'm going to do is instead of sort of having my initial, X, Y coordinates where X is horizontal and Y is going up here on the plane, what I'm going to do is I'm going to shift my coordinate system a little bit when defining this error. So I'm going to define one coordinate to be along the path of the reference that I'm tracking. So in particular, along the sort of forward direction of where the car is pointing along the reference trajectory. My second coordinate is going to be orthogonal to that. So it's going to be sort of, so you can sort of think of these coordinates as if I'm driving in a car, one coordinate is sort of along my lane, how far am I sort of ahead or behind where I want to be in my lane. And the second coordinate is sort of if I'm drifting left or right out of my lane. Okay, and then so we're going to define tracking errors based off of this. So my first tracking error, which we're going to call a long tracking error, we're going to denote with EAT, is going to be exactly that. It's sort of how much ahead or behind of where I want to be along the path is my car. The second tracking error, or component of the tracking error, is going to be what we're going to call this cross-tracking error, which again is sort of how much have I deviated outside of the lane that I'm trying to track. And then I think sort of naturally my my last coordinate error that I'm going to choose is just going to be the error in my heading. So this is going to be just the difference between the angle my car is pointing right now and the angle I want it to be pointing to be along the track. Okay, so let's take a second to think about what we did here when we were defining what these errors are. Okay, so as I said, I'm kind of going to go ahead and define a new coordinate system sort of centered around my reference, and in particular the point on my reference where I want my car to be. And so the way you can think of what we just did is we went from these sort of global coordinates, so my sort of natural X, Y heading coordinates, which are sort of the first coordinates you would think about representing your system in. And we transformed them to, maybe let's jump back here for a second, this new set of coordinates, where our new set of coordinates are instead of X, Y, Z, they're now defined in terms of EAT, ECT, and my heading error. So really what we did here is the way you want to think about constructing these tracking errors is really performing a change of variables or sort of a change of coordinates for your system. Where what we've done is, so if each of these errors is 0, that means that I'm at the origin and I'm exactly on top of the point I want to be on. So I'm exactly following my reference and everything is going good. So what I've sort of done is I've shifted the coordinate system for the representation for the system to a point where I always want to be driving my system to the origin. Okay, so now why do that? So this is potentially a somewhat complicated transformation. And the reason we want to do that we'll see a little bit later in the class, is that sort of putting the system in this representation is going to make it simpler to design controllers to drive these errors to 0. Okay, and so what we're going to do over the next few slides is we're going to understand, I think, just sort of systematically, how would I actually compute these particular tracking errors that I've just proposed here. And I think let's give you a little bit of a flavor for more sort of generically and more broadly how you go about computing these tracking errors. But I think one thing I want to emphasize here is, again, this is really how you want to sort of think about a lot of feedback control, and in particular defining these errors. It's really sort of constructing this representation which is sort of natural for your problem, right? So for a car, it's sort of very natural to define it in terms of how far along the path I am, how far off the path I am, et cetera, et cetera. And sort of peeling apart the structure of your system in this way will make it easier to control it in a little bit. Yeah. Okay. So we're going to do a little bit of a side on rotation matrices. These are sorts of objects which pop up all over in robotics and are very important, but we'll just sort of use them for our purposes today. So if you've taken a linear algebra class, you may have encountered these before, and we're going to find them a little bit differently than you may have seen before. Okay, so the basic idea behind a rotation matrix, and in particular, so rotation matrices hold in 3 dimensions, they hold in 9 dimensions. We're going to talk about rotation matrices just for the plane today. But rotation matrices, what rotation matrices capture is, let's say I have some coordinate frame. So here, this is again sort of my standard XY coordinate system for the plane that we're all sort of very used to working with. And let's say I have some other shifted or rotated coordinate frame, which we'll denote with X and Y prime, where in particular, to get this new coordinate system B, it's been rotated by theta degrees counterclockwise from my original coordinate system. So just one detail, in robotics, somewhat broadly, we define angles almost always in terms of counterclockwise rotations around the axis. We do that just to keep things consistent, and that's just sort of the convention that you want to have in the back of your head at every point in time. Okay, and so the sort of thing that we want to capture is really how do we sort of move between these 2 coordinate systems? And in particular, the rotation matrix R that we're going to define in just a second is the object which allows us to perform this change of basis between the 2 coordinate systems. And so the sort of utility for this rotation matrix is, let's say I have some vector, which we'll call V prime in my new shifted coordinate system. So this is given by X prime, Y prime. How do I represent this vector in terms of my original coordinate system, which we're going to note with just V? Okay, so this is the rotation matrix, and you'll see that it's parameterized by theta. Okay, so what that's saying is for every amount that I can rotate, I get a different rotation matrix, which is going to apply a different transformation when I'm moving between the 2 coordinate frames. And the way you want to think about this is the first column of the coordinate system captures how, the first coordinate of the rotation matrix captures how you change the first coordinate in your basis. And the second column captures how you change the second coordinate in your basis. And the way you want to see this is the way you use the rotation matrix is if I want to get the representation of my vector in my original coordinate system. So if I want to get what X and Y are to represent V, which is in my original coordinate system A, what I do is I take my rotation matrix and I plug in the angle of rotation that I had, and I multiply my vector in the perturbed coordinate system by this matrix. And what this does is it transforms V prime here back into V, which is this vector represented in my original coordinate system A. Okay, so just as sort of a point of notation, what we tend to call this rotation matrix here is the rotation of, okay, we're getting cut off here, but this is saying the rotation of B with respect to A. And the way you want to think about this is sort of, what this rotation matrix does is, how do I take something which is represented in B and represent it in A? Okay, so maybe just like sort of a natural question here is, so if this matrix tells us how to translate from B to A, how do I go the other direction? If I have a vector in A, how do I transform it to a vector in B? Anyone have any thoughts? Yeah. Multiply by the inverse. Yeah, that is correct. So I can multiply by the inverse. Can you think of another way where I could like sort of rearrange this and get the same effect? Yeah, so that's what we want. And so like okay, the inverse is like absolutely a valid way to do it. Do we have another thought on how we could do it?
Location matrix to the XY side and negative theta instead.
Yeah, exactly. Okay, so just to like put those two together, if I want to go from B to A, that is the inverse transformation of going from A to B. So we can just like use the inverse matrix to do that. Alternatively, if I want to get that inverse matrix, a way I can do that is by, so I moved theta degrees to go from A to B. And so if I want to go from A to B, I just plug in negative theta, and now I have my inverse. Okay, any questions about this? We're going to start using this. So the good point to pause, and do we feel like we understand what this object is doing? Okay. Okay, so let's go back to our tracking example. And again, remember, sort of our goal here is that we have a representation for our car and our reference in this original coordinate frame, this original XY coordinate frame. And again, you're trusting me when I say that eventually it'll be easier if we can sort of represent it in the coordinates that are sort of more natural to the reference. So what we want to do is we want to sort of convert this sort of natural notion of error that we talked about. So it's very easy to sort of calculate the distance in our XY coordinates between the car and where we want to go. So again, what this looks like is, so in my original XY coordinates, we have a vector which would describe the position of the car. That is the coordinate system for the car over there that we want to compute the error in. And we can very easily sort of just calculate the error between the car and our original XY coordinates. Again, this is the sort of the operation we proposed earlier, where we really just sort of subtract the reference from my current XY coordinates. So again, this is sort of just your like usual Euclidean like way of representing the error out in the plane. Okay, and now what we want to do is we want to take this error, which we're going to call EA. So in this case, A is our original coordinate system, our original XY coordinate system, as it was in the previous slide. And now what I want to do is I want to transform this into a vector representation of the error in coordinate frame B. Okay, so again, in words, that means that what I want is I want the rotation of B with respect to A, because again, I'm trying to represent this in coordinate B, which is the sort of shifted coordinate representation where I've decomposed it into along the track and across the track. I want to then multiply my error vector in my original representation A, so that when I multiply it by this rotation matrix, I'll get the error that I want in the new coordinates. Okay, so if we put all of these pieces together, this is what it looks like. So again, let's sort of like decompose what this looks like. So this is my error, or a vector representing my error in my original coordinates. So remember, this is represented in A. Now, unlike on the previous slide, because we want to represent this in B, what we're going to do is we're going to plug in sort of the minus angle, reflecting the difference between so we're going to sort of plug in the minus angle, which captures how you change, how you rotate A to get to B. Right, so again, in this example here, my heading of my reference in my original coordinate system, because I've sort of aligned my new coordinate system so that the x-axis in the new coordinate system is along this direction, really just the angle that my reference is pointing at captures the angle of rotation that I need to go from my original coordinate system A to my new coordinate system B. And so we put all these pieces together where we've used our reference and we've added a minus because we are now trying to sort of go from our original coordinate system A into our new coordinate system B. We plug that into the rotation matrix, and then we multiply the vector representation of our error to get the representation of our error and the new coordinates. Okay. So, okay, there's sort of a lot of steps where you're like swapping between this thing and that thing. Yeah, question?
Back.
Yeah. Yeah, no, that's a really good question. So yeah, that's actually a really important property of rotation matrices. So more broadly, rotation matrices are something called unitary matrices, and unitary matrices are exactly what you described. They don't sort of elongate your vectors or sort of perturb them in any other way. They keep them the same magnitude, and they do a very rigid rotation to them. And that's actually a really good question to ask because we're not going to encounter this today. But there's different cases where in order to make your errors or your error representations sort of work for different systems, you actually do need to sort of scale or warp things, but we're not going to go into that today. Okay, yeah, so just to sort of reiterate, we have all these different coordinate systems, and we had to sort of think through what coordinate system one thing is represented in, what coordinate system is the thing we want to get to represented in. But again, that's sort of the way you want to do it, right? We took a notion of error, which is easy to compute and very natural in our original XY coordinates. We figured out the right rotation or transformation to get it into the coordinates that we care about. And once we do that, now we have our tracking error in this frame of reference that we care about. Okay, right. And so again, if you sort of just like write everything out and fill in all the details, this is what it would look like. Okay, so again, we did all of that to sort of compute sort of the sort of translate the XY error into something which makes sense for the car. And again, we're going to define the heading error in just like the most natural way, where it's just the difference between the current heading of your car and the desired heading of your car. Okay, and so again, these are all just sort of written out here for you. And again, just to sort of beat a dead horse here, the way you really want to think about this is what I've done is I've sort of centered my universe on my reference car up there, and I've redefined where my car actually is in the world to be a sort of error or delta away from that point. And now that we've done this, what we're going to try to figure out is how we can actually sort of drive the system to that point and decrease this error over time. Cool. So yeah, I think we're about to transition. So just like any like high level, low level questions about tracking errors, how we compute them, why we care about them. Yeah.
As the car is moving around, so you define the how far away it is from the reference, or I guess like part of is wherever it is.
Mhm.
What
That's a really okay. That's a really good question, and we'll touch on this a little bit indirectly, and I'll try to answer this question in a little more detail in a little bit. And if I forget / do a bad job, ask me again. But at a high level, like yes. So another way of saying what you said is that these coordinates change with time. Okay, and so when we compute these tracking errors and we try to drive them to zero, um, we're going to start taking derivatives of these tracking errors because they're changing over time and we want them to go to zero. And those terms that you just brought up, which is we're trying to sort of track a moving target. The way that that changes is going to show up in those equations as we start taking derivatives. And so your controller will sort of be designed to account for those as it changes over time. That's a really good question. Any other questions? Cool. Okay, so like I said, next we're going to try to compute some control law, which takes in this error and drives the system to zero. So to just sort of make our lives sort of simple, we're only going to try to control the steering angle. So we're going to assume, just for the sake of right now, that our car is just going ahead at some desired speed. So really all we're controlling is sort of what direction are we trying to point the car. Yeah, so I think like all that to say, right, there's many controllers where there's many different design decisions, depending on how fancy you want to get, depending on what you care about when you're controlling your system, will sort of dictate which quantities you want to control. And again, we're going to sort of just look at sort of one error that we want to minimize to sort of get an intuition for some of the most basic types of tracking controllers that will drive these errors to zero. Okay. So we're going to, again, I think, talk about sort of the car case, but just like food for thought, does anyone have any ideas, like if I want to do this for like a much more complicated system, if there's more than one quantity that I'm trying to care about, like why that might be harder or more complicated than just sort of like controlling one quantity? Yeah.
Yeah, like knowing like everything, changing what the effect changing the things like, I guess maybe not for sure, like we just like one thing like increase to things or something like that. So we get both like often like the same.
Yeah, exactly. Yeah, it's a really good way of putting it. So what was just said is that so for example, like we're going to try to control one thing, but if you want to control a system where there's many things, where I'm trying to control like both the left leg and the right leg, well, those are coupled by the dynamics of the robot. And when I change how I control one of these subsystems, that'll change how I control the other subsystems. And so it gets a lot more complicated how you sort of stitch all of these pieces together. And so for reference, like I said, I know the people who did this and they spent like 2 months tuning this and sort of like configuring everything to get it to work together in very complex engineering robotic systems. There's a lot of like smart analysis and design decisions which go into putting all these pieces together. But again, I want to emphasize sort of like the basic building blocks we're going to use today, you sort of use in a loop over and over and over again to get to the point where you're doing something way more complicated like this. Okay. All right, so again, we're going to get to control now, which is very exciting. So for our purposes here today, just sort of like intuitively, we're just going to say, again, for our car example, like options for your control inputs are going to be things that you change about your system. You have control to change about your system over time. So these will be things like steering angle, speed. We're going to focus sort of on steering angle. And the way you want to think about these is what a controller does is sort of at every point in time, or maybe every sort of like discrete interval of time, where I update what my controller is, I look at where my state is, I look at the state of my system, I look at the error from where I am to where I want to go, and I sort of at this time think about, okay, how do I push my system back to where I want it to go? How do I drive this error to zero and sort of bring my real world system and my reference together? And again, there's many, many different ways you can do this. Like I did a whole PhD on this, and there's like many, many different design decisions that you can sort of get into when you're thinking about these sorts of things. Okay, so what we're going to do for the rest of today is learn about sort of the most ubiquitous controller in the world. And I would say that sort of you would struggle to find any sort of robotic system that includes like planes, cars, factory robots, the bipedal robot that I was showing videos of, which isn't using this controller at some point in its stack. Okay, so to motivate PID, let's think about maybe just sort of like the most simple possible controller we could possibly do. And so again, what we're going to do is going to sort of consider a simplified setting where we're just going to try to minimize the cross-tracking error. Let's assume we're just going straight. We're going at a constant speed, so we're not worrying about slowing up or slowing down or speeding up. And we're going to propose something which is called bang bang control. So what bang bang control does is it's the simplest thing you can possibly do. So if U max and U min are sort of the maximum values of my control that I can apply. So in this case, my maximum steering angle to the left or my maximum steering angle to the right. What this controller does is it says, okay, if my tracking error is negative, which in this case means that I'm sort of below the track, I'm going to steer as hard as I can to the left until I get back to the center. And then if I'm above it, then I'm going to steer as hard as I can to the right to get to the bottom. And this is a terrible idea. Does anyone have any thoughts on why this is a terrible idea?
So you also need to the two swings. So you swing left and then you cross the line and then you have to swing right again. And then you have to swing left and get this over.
Yeah, exactly. So you're going to be just oscillating all over the place. Like you're not going to actually drive your error to zero. Like you're going to end up doing something like this. For a lot of systems, this will destroy your motors. And if you think about this, if you're driving a car and you're sort of just like swerving back and forth, like as fast as you can, like what happens to your car? Oh, again, it's going to flip, which is a more extreme version of what I was going to say, which is your car is going to start vibrating, it's going to start shaking, it's going to start tilting. And again, we design our controllers with these very simple models. And generally, as you start to sort of like shake your like control systems more, it's going to start sort of like these like shakings introduce like new, more complicated dynamics, which make your model even more wrong. And so sort of a guiding principle for a lot of control is you want your control to be sort of as smooth and as nice as possible, because this stops your system from sort of just going crazy. Okay, so the sort of takeaway here is that just sort of being a tryhard and trying to just sort of go crazy and just sort of jerkily drive your error to zero as quickly as you can is going to lead to a bad time. So we're going to try to do something a little more sophisticated where the sort of effort or the control that we're applying is going to, in some way, shape, or form, be proportional to the errors that we're seeing. So again, just to reiterate, this is we're going to introduce something called like PID. This is used all over the place. It's used for cars, airplanes, industrial processes. You can't solve everything with PID. You can't get your Atlas robot to do a backflip just using PID. But you also can't get it to do it without PID. There are PID control loops in this and basically every robotic system that you'll encounter in some way, shape, or form. Okay. So what is our goal? Our goal is to take in our tracking control error and come up with a systematic way of choosing our control input U, so our heading angle, to sort of drive this tracking error to zero and to keep it there forever. Okay, so this is the PID control law, and there's a few parts to it. And we're just going to spend the rest of the class sort of peeling apart what they are and what they do. So this is the proportional term. And what you want to think of the proportional term as doing is sort of capturing the present state of your system. Okay, so what is this saying? What this is saying is, imagine my cross-tracking error is positive. If I increase this variable kp here, so these different k's are things that are called gains. So these are parameters that we're going to tune to get the performance we want for our controller. Basically what this says is, as my error gets bigger, I'm going to increase the effort or the control that I'm putting into the system. Okay, so again, like the bigger my tracking error, the harder I'm going to try to push my system back to where I want it to be. Okay. And in particular, notice that there's this minus sign here. So what this captures is the further if I'm sort of below where I want to be, I'm going to exert control effort in the other direction to sort of push my system back up and go where I want to be. Okay, so again, the proportional error captures what I want to do here. And the bigger I make this gain, the harder I'm going to try to sort of push my system back. The integral term is what captures sort of the past. Okay, so what the integral term captures is sort of all of the tracking errors you've seen from when you started controlling your system up to the present time. Okay, so the integral sort of captures historically, when I look back in time, have I always been like a little bit below where I wanted to be? Have I always been a little bit above where I want to be? And so can I use that information to just sort of correct for any errors that are sort of persistent over time? Okay, and the last term is going to be the derivative term, which involves the derivative of my tracking error. Okay, so when I have some quantity and I take its derivative, what I'm really doing is I'm trying to capture how is it changing over time. So to put that in a way, I'm sort of trying to capture what does the future of the tracking error look like? And so the derivative term ends up capturing the future. And so just sort of intuitively, again, so what the proportional term is going to end up doing is looking at where I am right now and trying to push my system back towards it. What the integral term is going to do is say, okay, I've been trying to push my system back to where I want, but I haven't quite got there. What can I learn from that and correct my behavior so that I'll sort of actually make it to my reference in the future? And the derivative term stops you from doing something called overshooting. So this is what we saw in the bang bang situation. And what the derivative term is going to end up capturing is basically if I'm moving towards my reference really, really quickly, if I don't slow down before I get there, I'm just going to overshoot it. And so what the derivative term ends up doing is sort of looking ahead and saying, hey, if I don't want to go flying past my reference and swerve past it again, I'm going to sort of want to ease up as I get there. Okay, so let's think about what happens if we only applied the proportional controller. And the situation is going to look a little bit similar to the bang bang approach. And the reason for this is I'm still going to sort of be doing the same thing that I was before, where I'm only really just sort of like, if I'm below, I'm sort of always trying to push up. If I'm above, I'm always trying to pull down. And the proportional term sort of like generally pushes you in the right direction. But because it's not accounting for what you're trying to do in the future, it will on its own will never sort of get your system to sort of converge all the way to the thing you're trying to do. Like you can actually like show this mathematically. We won't go into detail, but it's actually like impossible with just the proportional term to get exact tracking. That being said, the proportional term is okay. Oops, I said what was supposed to be on the slide. So again, the proportional term is again always just sort of trying to push you back to where you're trying to go. That doesn't mean it's not important to sort of try to tune the proportional gain appropriately. Does anyone have any thoughts on like what would happen if I set the proportional gain to be like really low? Like how would my system behave if I did that? Yeah.
Oh, take a really- it's like never in the future.
Yeah, exactly. So it might look something like this, where I kind of just very lazily, I'm kind of just going back and forth, like my gain is low, so I'm really not that upset if I'm sort of drifting far away from it. On the other hand, if I crank up my gain a lot, we sort of end up with something similar to the bang bang controller, where when I'm a little bit far away from the point where I want to be, I kind of freak out and I sort of part this way. And yes, I'm sort of being a bit more proportional. By the end of the day, I'm going to overshoot and then, oh crap, I'm all the way across the lane again. I'm going to go back and I'm going to have these sorts of oscillations. So in particular, so a lot of like control systems sort of have a limit to the control you can put into the system. So for our car, I can only turn the wheel so much. And so if I really crank up this gain here, like again, if I really crank up this gain, I sort of end up with the sort of bang bang behavior again, or something very close to it, where even when I have really small tracking errors, the resulting input that I put into my system is going to just be sort of dramatically turn as hard as I can to the left or as hard as I can to the right. And so the point is, it's one of the sort of like most natural things you're going to do when you're sort of tuning these controllers is like, okay, my system isn't doing what I want, so I'm just going to crank up my gains to try to push it back harder to where I want. And that won't solve the problem on its own because you're just going to end up with something like a bang bang controller and you're just going to be sort of chasing your tail and it's not going to go well. Okay, so now let's add in the integral term. So to sort of motivate this, let's think about the case where I'm out, crossing one of the bridges, going across the lakes, and there's like a really powerful wind buffeting me from the side. And I didn't really plan for that. So what the integral term does is it sort of looks at the effects of these sorts of things over time, where if I was just doing the proportional term, I might be, sort of pushing to some extent to the side, but that may not account for the like current conditions I'm finding myself in. And what I would want to do is sort of look back in the past and see, okay, I've been kind of drifting to the like side of my lane a little bit. And so what I'm going to do is sort of incrementally, slowly like increase how much I'm going to push to the side a bit. And that's exactly what the integral term does. Right. And so what the integral term does is if I have these sort of like steady state tracking errors, what it's going to do is it's going to look at those and say, okay, I'm not pushing hard enough to bring myself to where I want to go. And so the longer that I'm not there, I'm just going to keep pushing harder. And so I'm going to sort of wind up the control effort accordingly to slowly push my system to where I want to go. And so I think it's sort of helpful to sort of graph this out. So again, if this is sort of the behavior that you want to track here on the top here, if you just sort of put in a proportional controller, you might have something where you have some sort of steady state error like this, where you're not quite getting to where you want. And so what the integral term is going to be is sort of the area between where you are and where you want to be between these two curves. And you can sort of imagine that if I'm constantly not getting where I want to go, as time increases, the area between these two curves is getting bigger and bigger. And so the integral part of the controller here is going to get bigger and bigger. I'm going to be pushing harder and harder. So the word we like to use oftentimes to describe this sort of behavior is adaptive. And what that means is really I'm just sort of looking at how my system is behaving and updating my behavior accordingly by sort of pushing harder and harder to get back to where I want to go. Okay, so I have 2 minutes left, and let me give me 1 second. Okay, so yeah, we'll just sort of leave it here, and Abhishek will pick up with this on Friday. But we'll just very quickly talk about what the derivative term does. So again, what the derivative term does, if we add this into the proportional term, is what it says is, let's say my tracking error is 0, or excuse me, a lot less than 0, so I'm below where I want to be. And if my derivative error is zero, so that means I'm sort of, pointed in the direction I want to go, then my derivative term isn't going to do anything, and I'm going to be back mostly looking at my proportional term. Okay, so if I'm sort of pointing in the right direction for where I want to go in the future, the derivative term doesn't do anything. But now I've sort of turned where I'm getting closer to my reference trajectory. So my proportional term is doing a bit less, but now I'm sort of aggressively charging towards my reference trajectory. Now, all of a sudden, this term is going to pick up. And because it's going to be greater than 0, what it's going to do is sort of put the brakes on. And whereas this term is trying to push you up and go closer, in this case, this term is going to be sort of trying to push you down and keep you from overshooting. Okay, so I think we'll stop here just in the interest of time. I think Abhishek will probably walk through this a little bit more detail. And what you're going to learn next class is sort of some of the nuances of sort of how you tune all of these things together. But again, with that, thanks for coming in on a snowy day, and I'm happy to stick around if anyone has some questions after class.
Thank you.